detector system requirement.
To speak at this workshop. And my talk today will be, I would say, complementary to what Giovanni said 2 days ago. I will talk about pretty much the same models of deformed relativistic kinematics today, but I will focus on possible effects which can characterize these scenarios. And these effects are Planck scale decoherence and the formation of discrete symmetries. So essentially, the story I will tell you about today dates back from what I call the prehistory of quantum gravity phenomenology. And in particular, referring to this paper by Ellis, Agalin, Nanopoulos, and Srednitsky, where essentially what they did, they proposed to test the possibility of a fundamental decoherence using neutral counts and neutron interferometry. Essentially, their motivation was the proposal by Hawking that essentially the quantum radiation from black holes and their eventual evaporation should lead to a loss of quantum coherence. Okay, what I mean more in detail. Let me be a bit more specific. So we know that in ordinary quantum theory, evolution is unitary. So if we have a density matrix describing an initial state rho n, then we have an evolution, a unitary evolution operator S, which produces a final density matrix rho final. And so if the initial state is pure, namely if the trace of this initial density matrix squared is equal to 1, then obviously by this kind of formula for the evolution, we get that the final density matrix is also pure, since the trace of the squared of this final density matrix is also equal to 1. So in this sense, purity of a quantum state is an eternal property in ordinary quantum mechanics. So if we have to take seriously the proposal by Hawking that quantum radiance, black hole quantum radiance should lead to a loss of unitarity, a loss of unitary evolution, namely that we can have pure initial states, pure quantum states evolving to mixed states, then something in this formalism must change. And the proposal by Hawking was that in quantum gravity, this evolution operator S should be replaced by what Hawking called at the time superscattering operator, and which was denoted by the $sign. And so now this is the evolution equation, different from the standard ordinary unitary evolution. And this equation should allow the trace of the square of the final density matrix to be less than 1, so that we can actually evolve pure states into mixed states. So the idea of this paper of Ellis et al., which I was showing in the previous slide, was to explore the potential phenomenology of this decoherence, of this model of decoherence. And what they did was to focus on a differential form of this evolution equation, where basically the time derivative of the density matrix is no longer given by the commutator of the density matrix with the Hamiltonian of the system, but by this more general form here with this operator H slash. What does this operator look like? This was explored by Banks, Peskin, and Saskind in a paper which came out about the same time as the original paper by Ellis et al. And what they did here, they looked for the most general form for this evolution equation, assuming that the evolution preserves hermeticity of the density matrix and the trace. And by doing so, they basically obtained this equation, this most general evolution equation, which was actually already known in the literature in the study of open quantum systems in the late 70s. And this is called the Lindblad equation or Lindblad-Kosakovsky equation. So here we have the usual von Neumann evolution term here. And this is the non-trivial part, in which we have here H alpha beta, which is an emission matrix of constants. And this operators Q here are basically we consider here a finite dimensional Hilbert space. These are this is a basis. The Q alphas comprise a basis of emission matrices. So over the years, people have questioned if there are actually models of quantum gravity which predict, I mean, top to bottom models of quantum gravity, which can predict this kind of effects, okay, this kind of deviations from ordinary von Neumann quantum evolution of the density matrix. And basically, what I will show today is that there are some Planck scale modifications of these symmetries, which I will discuss in detail in the next slides, in which such generalized quantum evolution can be realized. And the main ingredient of these models is that the momenta describing the quantum particles live on a non-abelian Lie group. Okay, and the curvature of such group manifold is set by an energy scale which we call kappa, and which we can think of as setting the Planckian energy regime. At the algebraic level, these models are characterized by a deformation of the action of translation and Lorentz transformations on states and observables of the system, as we will see in detail. And these deformations actually turn out to affect basic notions in your quantum theory, and as I will show, they will lead to a potential fundamental decoherence and the deformation of discrete symmetries and the CPT. So here's some references. The stuff I will be talking about has been developed in these papers by myself and my Polish collaborators in Warsaw. So let us be a bit more concrete. So the idea behind these models of deformed discrete symmetries is that there exists some flat space limit of quantum gravity in which we can think of h bar, Planck's constant, and Newton's constant going to 0 while the ratio is keeping fixed. And this ratio, this fixed ratio, will set a fundamental constant in our theory. So this Planckian energy kappa in our models will introduce an observer-independent energy scale, and this actually happens really at the algebraic level of the models. We can think of the resulting quantum Minkowski space-time limit as a space-time described by a non-commutative algebra of functions. And in our particular models, this algebra of functions will, these coordinates will close a Lie algebra. And this non-commutative this non-abelian Lie algebra will become abelian in the limit kappa going to infinity. And the formula, as I anticipated, the four momenta describing this, the kinematics of such particles will become coordinates on a non-abelian Lie group. This might be a little bit esoteric to the non-specialists, but it turns out that this scenario is realized for quantum gravity in 2+1 space-time dimensions. Indeed, in this case, when the cosmological constant vanishes in this simplified three-dimensional case, we know that all solutions to the Einstein's equations are essentially look like Minkowski space locally. And the theory is topological. In 2+1 dimension, general relativity does not admit local degrees of freedom. So particles, point particles coupled to this theory are described by conical defects in space-time. And it turns out that their momenta are elements of the SL2R Lie group. Okay, this has been shown in this classic paper by Matt Schul and Welling back in 1998. And it turns out that upon quantization of these conical particles, the field theory describing the quantization of the quantized relativistic particles is a non-commutative field theory in which the coordinates obey the SL2R Lie algebra here. Okay, and you see here the appearance of the constant kappa, and in the limit of kappa going to infinity, this becomes an abelian algebra, and here kappa is proportional to 1/g. Okay, so now this is all well and nice, but we are in a universe. We live in a universe in which, at least apparently, we have 3+1 dimensions. So can this scenario be happening also for quantum gravity in 3+1 dimensions? Well, in 3+1 dimensions, generally is certainly not a topological theory. We have gravitons and also all that stuff. So, however, it has been speculated that UV completion of quantum gravity might be indeed a topological theory. Okay, these are just speculations. And it turns out that particles coupled to gravity in 3+1 dimension can be formulated as a topological BF theory, and can exhibit a deformation of kinematics similar to the 2+1 dimensional case. This is work by Kosakovsky and Artyom Starodubtsev some years ago. However, we must be honest and say that a rigorous link between deformed kinematics and quantum gravity is far from being established. But these models of deformed kinematics can actually turn out to be very useful to develop some effective models of Planck scale physics that we can use to extract phenomenological predictions. Okay, so the model I'll be focusing today on is the kappa-Poincare algebra. Probably Giovanni already talked about it 2 days ago. And such model was introduced basically 30 years ago by a group of Polish mathematical physicists who had in mind at the time to use the tools of quantum group theory to deform the relativistic symmetries in order to be able to introduce at the algebraic level a UV energy scale, kappa. So the picture is the following. The four momenta of our particles are given by coordinates on the Lie group AN3. So what is the Lie group AN3? Think of the 5-dimensional Lorentz group SO41, and this can be written as this factor of the 4-dimensional Lorentz group times this group AN3. And as a manifold, this Lie group is nothing but half of the Sitter space. So you can think of your four momenta as living on a curved momentum space with constant curvature. So this is the condition in embedding coordinates which sets which describes the Sitter hyperboloid, and this condition here selects the half of the Sitter space, which is the manifold associated to this Lie group AN3. Okay, the coordinates dual to this momenta living on the Lie group AN3 are non-commuting objects, and essentially are the generators of this Lie group. So they belong to the AN3 Lie algebra, and this is the commutator of this Lie. These are the commutators of this Lie algebra. You see, spatial coordinates commute among themselves, while time coordinates do not commute with space coordinates. So in order to understand how these structures alter very basic notions in quantum theory, let me recall what an elementary particle is in quantum field theory. Essentially, one particle states in ordinary quantum field theory are given by irreducible representations of the Poincare group. So normally we describe basis of this one particle Hilbert space using eigenstates of translation generators. So we are our familiar cats here labeled by the momentum, the form momentum the particle carries. Okay, and now you can construct a dual Hilbert space in the space of brass. And the theory, the representation theory of the algebras tells you that the action of the same generator on this dual space from the left must give you minus the eigenvalue of the for the bra. Okay. Bringing this eigenvalue to the right, we can rewrite this action from the left of P mu on bras as an action from the right with another operator which I call S of P mu, which I call the antipode of P mu. Okay, so the antipode of this generator describes the way it describes essentially the dual representation of for this P mu. Now, starting from one particle Hilbert space, you can also produce multi-particle states by taking tensor products of one particle Hilbert spaces. And we know that the action of translation generators on these guys is the usual Leibniz action. So first I act on the first particle and then act on the second particle, and these can be encoded in an operator on P mu called the coproduct, which I denote as delta of P mu. Okay, so we have these two operators, the antipode, which gives me minus the generator of translations, and the coproduct, which describes the Leibniz action of the. Okay, I think the host muted me for a second.
It was a mistake. Sorry, Michele.
Okay. So the nice thing, I mean, these are very simple things, and tell you that essentially these antipode and coproduct are objects which belong to the theory of Hopf algebras. So these are notions of Hopf algebras, which are built in our everyday quantum field theory, if you think about it. And actually, it turns out that these notions are enough to derive the action of, for example, translation generators on other operators. Let us take, for example, this projection operator on a state K. Now you can act, if you want to act on this exterior product here, what you do, you first apply the Leibniz rule. So first act on the first and then on the second. And then you apply the so-called antipode when acting on the bra, okay? And what you obtain is simply the usual adjoint action of an operator on another observable, or let's say a symmetry generator on another observable, okay? And this is I just did this for the projection operator, but using the spectral decomposition of all observables, you can actually derive this action on every observable of your theory. Now, the deformation of symmetries gives you a generalization of this basic notion. Let us see how. So in the deformed kinematics scenario, the cats now describing your particle are labeled by elements of a non-abelian Lie group. Okay, and the P mu here, the eigenvalue of the actual translation generators on the states is given by some coordinate functions on the group manifold. Okay, so P mu here would be just given by some set of coordinate functions on the Lie group. For the action on bras, now you will have that this guy will read the coordinates of the inverse group element here. And on multi-particle states, this guy will read the coordinates of the product of the two group elements, labeling the the particle, the individual particles, okay? And this has a very non-trivial consequence because as Giovanni told you a couple of days ago, now the total momentum of the two particle state here will be given by a non-abelian sum. And so the state pi1 tensor pi2 will have a different total momentum than the state pi2 tensor pi1, okay? So essentially this reading of the inverse coordinates of the coordinates of an inverse group elements for the action on bra, and this reading of the coordinates of a product of two group elements when acting on two particle states basically is just encoded in the fact that you have a non-trivial coproduct and antipode for your generators. And the key point is that the action on operators, which I showed you on the previous slides, will be deformed, okay? Let us see this in specific case. Let's consider the translation generators associated to embedding coordinates on your the system momentum space. So I here just write the coproducts and antipodes for time translation and space translations at leading order in the deformation parameter kappa, okay? So this particular incarnation of the kappa Poincare algebra is called the classical basis because in this model, the action of the Lorentz transformations on momenta is undeformed, and also the mass shell condition is undeformed, okay? So all the non-trivial structure is here, is in the way the generators act on multi-particle states and on the dual spaces, okay? So you can just go ahead and basically redo this little game here with the non-trivial coproducts and antipodes now. And what you will obtain, sorry, for the action of P0 on an operator. So you do the calculation of the adjoint, of this deformed adjoint action of P0 on the density matrix. And what you will have exactly, well, not exactly, some sort of equation which looks like a Lindblad equation. Notice that this is non-symmetric. There's non-symmetric form of the Lindblad equation because we have only the term with rho p squared appearing here. We don't have the p squared rho term. But this non-symmetric form of the Lindblad equation is necessary if we consider the fact that the adjoint operator acting on this equation must include involves actually a non-trivial antipode, okay? Also, this very strangely looking evolution equation is covariant. Indeed, the action of boosts on operators is also deformed since the coproduct and antipode of boosts is deformed. And so this is the way the action of boosts looks on a state, on a density matrix. And it turns out that this deformed notion of covariance is satisfied by this Lindblad equation, okay? So could this deformed quantum evolution could be tested in some way? Well, you know, there's a long history of attempts to measure fundamental decoherence using precision measurements in the neutral count factories, and especially in the Chloe and Chloe 2 experiment in Frascati in Italy. And so could we attempt to use this data to set bounds on this deformation parameter kappa? Well, I mean, that is non-trivial at the theoretical level, because you know what I showed you holds essentially for a free non-interacting quantum field theory. So one should first work out how this kappa deformation should actually enter the description of the evolution of neutral counts. And this is, let's say, it has been on my agenda for quite a while, but the progress so far has not been very consistent. Could there be also other experimental windows which will allow us to put bounds on this deformation parameter kappa? Well, maybe neutrino oscillation. I've heard in recent conferences on this quantum gravity phenomenology and the multi-messenger approach that people have been looking at tests of fundamental decoherence using astrophysical neutrinos. So, well, we'll see. We'll see if this will bring us somewhere. The interesting thing is that, and this is actually a natural question, is that do these new structures, which I just talked about, affect in some way also discrete symmetries? And why am I asking this question? Well, because a long time ago, Bob Wald pointed out that if you actually have some quantum gravity-induced fundamental decoherence, you basically would undermine the basic assumptions underlying the CPT theorem. And then your CPT operator would not be well defined at all if you have this kind of fundamental decoherence. And indeed, as I mentioned in the previous slide, there is a long and venerable literature of concerned with searches of fundamental decoherence and violation of CPT using neutral counts. Okay, so these effects are taken together in these works. As I showed in my work with Kowalski-Glickman, it turns out that the non-trivial antipode, which I just showed you in the previous slides for the generators of Poincaré, of kappa Poincaré transformations, play actually a huge role in defining discrete symmetries, and they lead to a notion of deformed CPT transformation. This is to be contrasted with the idea of Wald that in the presence of some fundamental decoherence, your CPT operator is not defined at all. So the idea is that we use basic physical requirements and some algebraic consistency to define the action of parity, time reversal, and charge conjugation. Let's see how we do this. So for parity, we stick to the physical requirement that essentially the momentum of a particle plus the total momentum, total linear momentum of the particle plus its parity image should vanish, okay? And this basically forces you to consider the parity map of the linear translation generators, the spatial translation generators, to be the antipode. So if I do the map, the parity of pi, instead of minus pi, will be the antipode of pi, okay? Then we use algebraic consistency. So if you use the antipode for the linear translation generators, the spatial translation generators, you have to use it for all the generators of the Poincaré algebra. Otherwise, you will not longer close the algebra, okay? So, and then we use also a correspondence principle that in the limit kappa going to infinity, we recover ordinary parity, okay? So this leads to the following form of the parity map on the Poincaré generators. You see, so this is the parity map of pi is this guy here. So you have this is leading order in the deformation parameter, okay? You can see that the deformation affects space and time translation generators and boosts, but it leaves unaffected the generators of rotations, MI here. To define time reversal, I require, using again this correspondence principle, that in the limit kappa going to infinity, time reversal should flip the sign of MI. So the definition I have here is similar to the parity one, okay? But now I have a minus sign here in front of the map for boost generators, and I have a plus sign here in front of the map for translation generators. Charge conjugation is a bit more subtle. So to see this, let us recall that for a complex scalar field, for example, if we have the one particle Hilbert space, then the complex conjugate space is the one antiparticle space. So an ordinary charge conjugation maps states on the one particle state. Here I've written an element of the one particle Hilbert space essentially as a function on the mass shell, okay, here. And charge conjugation maps this element of the one particle Hilbert space into this element in the complex conjugate space. Now, it turns out that the complex conjugate Hilbert space is essentially isomorphic to the dual Hilbert space. So we know that symmetry generators, according to what I said before, should act on this space via the antipode. And this, imposing again that in the limit kappa going to infinity, one recovers usual charge conjugation, leads to this form this action of the charge conjugation operator on the generators of the Poincare group, of the kappa Poincare. So putting all together, we can have finally this form of the CPT operator acting on the generators of the Poincare group. You see, we have a well-defined notion of CPT map, okay, but it is deformed. So it contains terms which ordinarily are not there and which disappear when kappa goes to infinity. Our deformation parameter goes to infinity. So the main message is that if you have a non-trivial antipode, the action of the CPT operator is deformed. And again, this is different from the violation of CPT suggested by Wald back in 1980, where that violation of CPT is essentially associated to the fact that the CPT operator is not well defined. So the deformed CPT map lead indeed to the prediction of different lifetimes between particle and antiparticle, okay? Normally, you know, if you have the lifetime of a particle and antiparticle, they are equal, okay? Where by gamma here, I denoted the particle inverse lifetime. Now, if I look at my system of particle and antiparticle boosted, the gamma factor, which is responsible for the time dilation, is given by E over m for the particle. And in our deformed case, for the antiparticle will be given by the antipode of E over m of the mass of the particle. So will be given by this expression here, different from E over m with this corrected term. Okay. So the decay probabilities for particle and antiparticle become as follows, and they differ from each other. You can actually, using what we did in this paper with Kowalski, Diekman, and Wojtek, we looked at the precision data on muon lifetimes to actually set bounds on the deformation parameter kappa, okay? And with data from LHC, so we're looking at energy of the linear momentum about 6.5 TeV, you get that the bound on kappa is about of the order of 10 to the 14 GeV, and expect that in the future circular collider, this where the energies could reach the 50 TeV, this bound could be pushed up to 10 to the 16 GeV. Okay, so let me just summarize. What I wanted to show in this talk is that in models of deformed Planck scale kinematics, which are popular in the quantum gravity phenomenology community, we can have essentially effects of fundamental decoherence in some specific model of this deformed kinematics, and we can have deviations from ordinary CPT invariants, okay? And essentially, the phenomenology associated to this effect is largely unexplored. So I urge the experimentalists in the audience to suggest as possible ways to test this phenomena and you know, to take advantage of these possible new windows on the world of quantum gravity. Thank you.
Thank you very much, Michele, for this very nice talk. So I would, at this point, ask if there's a question from the audience. So if there's no question, I would eventually ask Michele if he can comment more about the deviation from the CPT invariants and the possible phenomenology that could be linked, let's say, to the constraints that can be posed about Pauli exclusion principle violating transitions. If you can comment a little bit more about this point from the phenomenological point of view.
Yes, from the phenomenology point of view, not really, because I'm not a phenomenologist, but indeed, I mean, okay, so the thing is that I didn't mention the fact that there is a bit of controversy concerning our definition of deformed discrete symmetries, which I given here. Okay, so this proposal that we made with Kosakovsky has been criticized, since I didn't show you here, but essentially this, for example, this parity operation here is not idempotent. Okay, so if you apply twice parity, you don't get back the original momentum. Okay, so is this a problematic feature, or is this a feature which could lead to some interesting phenomenology? We don't know. There have been alternative proposals of discrete symmetries in this setting, where either one proposes to have ordinary discrete symmetries and or variations on the theme. So these discrete symmetries business, let's say, has not been definitely settled in this field. Okay, now, so I think it's a bit premature to start asking questions about the possible consequences for Pauli exclusion principle. Even though I think probably the most promising avenue to look for effects which might affect, sorry for the Pauli exclusion principle, is the stuff that Giovanni talked about on Tuesday. So essentially the fact that in these models, you seem to be forced to have a non-trivial Fock space, and you, Antonino, know this very well, right? And so that basically states containing many fermions might have to be described by a deformed Fock space, where you have this proliferation of different n particle states, all with different momenta. Okay. So that, I think, remains a very intriguing possibility for setting bounds on these models of deformed relativistic symmetries from phenomenology.
Okay, thank you very much for this comment. So is there any question for Michele? Otherwise, I would kindly ask Andrei Derevianco to start sharing.